Good morning, scholars. Welcome back to day 3 of what I would define to be the foundation of sketching polynomials. Today we're going to be talking about this new term known as the multiplicity of a factor and its subsequent effect on the shape of a graph so that we could use zeros and multiplicities to create a rough graph of a polynomial function given in factored form. I'll know I've got it when I can use zeros and multiplicities to sketch a graph of a polynomial. If at this point you are starting to feel like you don't have a solid grasp of what we are discussing, please make sure that you reach out. This content, I cannot stress enough, is a significant portion of what you will see in calculus. So we define this new term, multiplicity, of a factor to be the number of times the factor occurs when a polynomial is written in factored form. We can start with this top left one, right? We can see that this expression is y equals x minus 3 to the second power. So that term, that factor of 3, would have a multiplicity of 2. If we look to our bottom left graph, we can see that the multiplicity is changing, which also is having an effect on the behavior surrounding the root as compared to the original in the top left-hand corner. So I'd like for you to kind of share some dialogue with your peers and decide on 2 things that you notice and 2 things that you wonder about the algebraic expressions and the subsequent effect that it's having on the graph, taking into account the multiplicity of each factor. For the remainder of this lesson, we will spend a lot of time putting into practice sketching polynomials, right? So this involves the end behavior. This involves the degree of the function. This involves this idea of multiplicity, this idea of the leading coefficient, constants, zeros, so on and so forth. I will model slide 4 so that you have something that you can go back and reference. But for the polynomial function b of x, I know that when I multiply this function through, the degree of the function is going to be 3. The zeros are going to be -2 and +2. I'm going to have a 0 here, a 0 there. If I wanted to determine the y-intercept, I could substitute 0 into x. I have 2 times -2 squared, which will give me 2 times 4, which is 8, but the negative outside will still yield a -8. I know the overall leading coefficient will be negative, so with it being a degree 3 function, my end behavior should fall from left to right, and that's what I would like to define the behavior as. So as x gets larger and larger in the negative direction, the output of the function will increase to infinity as x gets larger and larger in the positive direction. The output will decrease to negative infinity. So as I come to my first x-intercept, at these points I would need to take into consideration the multiplicity of each factor. To this point, we've just been able to kind of go straight through our roots. And for this particular context, that is a perfectly valid move, right? Because then we enter through the y-intercept. However, if we continue through our second x-intercept at x equals 2, notice, even though our end behavior is supposed to finish at negative infinity, I am now on the opposite side of the x-axis, which I cannot pass back through without an x-intercept. So at that particular x-intercept of 2, I need to, instead of going straight through the x-intercept, I need to bump that particular x-intercept. And I know my graph is extremely rough, but once again, we're sketching the shape of the graph, not giving a precise computer algebra software representation of the graph. The reason why I know that I'm going to bump that particular point is due to the multiplicity of that particular root of being 2 or an even amount of times it occurs. I'm going to take this entire function and substitute into Desmos. I don't think you can actually see that screen, so that would be useless, which is unfortunate. But when you substitute that function into Desmos, if we zoom in specifically on the x-intercept of 2, we can see that it is mirroring quadratic behavior. And I know where we can look. We can look at our warm-up. Right? At this x-intercept of 3, we have parabolic behavior. Whereas in the event that we have an odd degreed function, the behavior is going through mirroring a linear style of behavior. If you take a look at both the top right and bottom right functions, you can see the same holds true, that there is parabolic behavior, this bump-like effect at one x-intercept, but linear behavior, or straight through behavior at the other. So these, right, this now becomes our curve sketching stew. Everything that we have to consider: the zeros, the y-intercept, the degree, the leading coefficient, the end behavior, the multiplicity. Okay, so I've just named 6 different things to consider. I might, if I were you, make a list. That way you can just kind of check off your list. Our final slide has you speculate to sketch a graph for a polynomial function that has 3 different zeros, but the function is greater than 0 for the entire domain. What is the smallest degree the polynomial could possibly have? 0, 1, 2, 3, 4, 5, 6, 7, or larger than 7. And once you make your selection, be sure to justify your degree choice. What is a possible equation for the polynomial that you sketched? And we'll pause and pick up with a riveting discussion together in class.